All right, welcome to another set of notes. We're going to talk in these notes about significant figures, or sig figs for short. All right, so let's start off with our first question. What are significant figures and why are they important? Now, we're talking about significant figures. We're not talking about people in history or whatever. Figures is another name for numbers. Okay, so significant numbers. Now, we use significant numbers because in science, it'll tell you exactly how precise your measurements are. And we've been working with measurements the last couple of days in class and the last couple of notes with our measurement notes, measurement lab, unit conversion notes. Tomorrow you'll be doing unit conversions in class. So we're going to be working a lot with measurements and numbers, and so we need to figure out exactly which digit you round to, which place in the digit you round to, and it'll also tell you how precise your measurements are. Okay, so our first question is why are they important? Okay, so scientists tell us how precise their measurements are by the number of digits they report. The number of digits they report are what's called significant figures. We haven't talked about precision and accuracy yet in numbers, but it tells you how good or how detailed of a measurement you have. Okay, so here, let me give you an example. So in our example here, 3.54 grams is more precise than 3.5 grams. Okay, so you'll be using actually two different balances in chemistry. One of them is a 2-digit after the decimal place scale, and then the other one shows just 1 digit after the decimal place scale. Okay, so if you measure something on the 1 digit after the decimal, you'll only get 1 digit. So we might, if you measure a pencil or something and it might be 3.5 grams, if you put that same pencil on the 2-digit scale, you're going to get 3.54, which is more precise, okay, because we have they've given us more digits of measurement there to work with. So that's what I mean by more precise. So the measurement 3.54 grams has more significant figures in it than 3.5 because it's a more precise number. Okay. Now, when we work with instruments where it's not digital, it's like where you have to read tick marks and measurements, like on a graduated cylinder or on a ruler or a meter stick. Okay, one of the rules for significant figures is that you include all of the digits that you can actually read on the instrument, plus you can estimate 1 digit kind of between the markings, and that's what I had explained in the measurement notes, your very first notes from before, okay, where we had that piece of string, and we knew it was between 2 and 3 inches, so we kind of estimated one of those digits. We estimated it was 2.5. Okay, so let's put that in our note. So this estimated digit, when you're reading digits off of a non-digital instrument, is just gonna, kind of reinforces us to make that estimate. If it is between 4 and 5, say 4.5. Okay, it's totally okay to do that. Okay, and that digit will count as significant. Okay, so let's get into our next question, which deals with, okay, how do I know which digits are significant? Okay, when trying to determine which digits or numbers in a measurement are significant, we do need to know that not all the digits will be significant, because some will be just placeholders. They'll be holding the place to make it a really big number or make it a really small number. So that kind of sets into play some rules that we have to think about when we are figuring out which numbers in a measurement are significant. All right, so our first rule is that the numbers or the digits 1 through 9 are always significant. Okay, so they are always counted as significant or important in a measurement. So if 1 through 9 is always significant, then the only one that's going to be tricky are the zeros. Okay, and so those zeros are going to be the tricky, pesky kind of little guys. So let's talk about those zeros for a sec. Okay, so with those pesky little zeros, there are just two rules that you actually have to know about those zeros. Zeros that are what we call sandwiched, which means that they're between digits that are 1 through 9, are significant. So we do count them. Okay, so in our example, 109, okay, that number 109, the zero in between there that is sandwiched, this zero does count. It is significant. So we would say there's 1, 2, 3 significant figures, okay, or 3 sig figs in this number. Okay. However, if the zero comes before the number or after the number, meaning that they are place-holding zeros, those ones are not significant, so they are not counted. Okay, so we have two examples here. We have an example of a really small number, 0.00076. Okay, in this case, the zeros out in front are just placeholders. Okay, to tell us that it's a small number. So these zeros are not going to count. So in this number, there are only 2 sig figs. Okay, 2 significant figures. All right, and if we take a look at this third example, or the second example for this one, 153,000. Okay, so again, we've got placeholder zeros, but now they're in the back. Okay, so these zeros here are just to tell it's a really big measurement or a really big number. So these ones do not count either, okay, because they're placeholders. So in this number, okay, there are only 3 significant figures, or 3 sig figs. All right, so that is the general rule. If that makes sense to you and you know what placeholder zeros mean, then go with it. It's the simplest way to figure out which or how many significant figures there are in a number. Now, if you're not quite sure, or you really, kind of get the zeros messed up, I do have a second way, and it's more like of a visual way. So if you're a visual learner, it's more of a visual way to take a look at sig figs, and it's what we call the Pacific Atlantic rule, and we'll go over that one right now. Okay, so this rule again is more visual, and it has to do with oceans. Okay, so obviously you kind of figured out here that the Pacific is referring to the Pacific Ocean, and then that's obviously on the west coast of America. So if we take a look at this globe here with the United States right there in the middle, the Pacific Ocean is on the left-hand side, okay, or the west coast, and the Atlantic Ocean is on the right-hand side, okay, or the east coast. And so what we're going to do is just kind of keep that visual in mind as we ask ourselves the key question for this rule. Is the decimal place present? See, there's a P there. That's important. Present or absent. Okay? Present and absent have the P and the A from Pacific and Atlantic. So we're going to keep that in mind as we go through this rule. Okay? Okay, so the first part is if we look at a number or a measurement and the decimal place is present, okay, so we've got that P for present, what we're going to do is we're going to read that number from the Pacific side, okay, that means from left to right, so starting on the Pacific side and going towards the Atlantic side, okay, and we're going to start counting all the digits as significant when you get to the first non-zero digit, okay? So let's go over an example. All right, so here's an example. if we have 0.0000875, okay? So we have this number here, and we see that the decimal point is present. So we're going to start on the Pacific side over here, and we're going to read that number from left to right, from Pacific to Atlantic, and we're going to start counting the number of significant figures when we get to the first non-zero digit. Okay, so this first one is a 0, doesn't count. Next digit, 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 8, this counts. Once we start counting, we don't stop till we get to the end. Okay, so we have 1, 2, 3 sig figs in this example here. Okay, so we have 3 significant figures. Now we see that all the zeros in front were placeholder zeros, so that rule works in coherence with the Pacific Atlantic rule. So this is more just a visual way, again, to visualize those placeholder zeros as not counting as significant. Okay, so that's if a decimal is present. Now let's take a look and see if the decimal is absent. Okay, so the Atlantic part of the rule says that if the decimal point is absent from a number, if there's no decimal point in the number or the measurement that you are looking at, you're going to read the number from Atlantic to Pacific side. So you're going to start at the Atlantic and read it the opposite way and go to the Pacific side. So you're going to read it from right to left now. Okay, and again, you're going to start counting all the digits as significant once you hit that first non-zero digit. Okay, so here's an example. If we had that number, let's just say 248,000. Bam. Okay, no decimal present. Okay, so what we need to do then is read the number. Since it's absent, okay, we read the number from the Atlantic side to the Pacific side, okay, and we start counting all the digits as significant when we get to the first non-zero digit. So this first 0, doesn't count. This next digit's a 0, doesn't count. Next digit's a 0, doesn't count. Okay, next digit is an 8. This one counts, and everything in front of it counts as well, because we just keep on going. So 1, 2, 3. So this number has 3 significant figures as well. Okay, and again, it's reiterating or giving a nice visual for these zeros here that are just placeholders, telling you, that it's a big measurement, not just 248, but 248,000. Okay, all right. So now that we know the rules of trying to figure out, what are significant figures, we're gonna take a look at rules when we are adding and subtracting numbers and multiplying and dividing numbers. Because what this is going to do, it's the key answer to your question that you will have one of these days in chemistry. What do I round to? Okay, you're gonna have a calculation. You're doing a calculator, and you'll be like, well, what do I round to? Okay, you will never have to ask me that question once you know these rules. We're gonna start with adding or subtracting. All right. So our third question here is what do I round my answer to when adding or subtracting numbers? Okay, so in adding or subtracting, the key is the decimal point. Your answer is going to have the same number of digits to the right of the decimal point as the value with the fewest digits to the right of the decimal point. Sounds really confusing, but let's take a look at an example. Okay, so let's say that 3 different groups were given a shoestring to measure out, And one group got 28.0 centimeters. Another group was working with a more precise ruler instrument and got 23.538 centimeters. And the third group got 25.68 centimeters. Okay, so we can see here that there's decimal points in all of these numbers. And so what we're going to be concerned with is how many digits to the right of a decimal point there are. All right, so we can see that the first number has 1 digit to the right, the second number has 3 digits to the right, and the third number has 2 digits to the right. So our rule is that our answer must match the number of digits to the right of the decimal as the measurement with the fewest. And so this measurement here has the fewest numbers to the right of our decimal. All right, so when we do this math computation, we have to round to 1 digit after the decimal point. Okay, so if we do this, we're going to end up with 77.218 centimeters. Okay, however, because not all of these measurements were as precise as one another, we can only be precise in our answer as the least precise measurement, or the one with the fewest digits to the right of the decimal. So we can only round to 77.2 centimeters. That's as precise as we can go, because that first group there only had 1 digit after the decimal point. Okay, so that is going to be our answer. So when we get huge something in our calculator and you ask me what do I round to, I'll just tell you, use your sig figs. Okay, let's take a look at one more example for adding or subtracting. Okay, so in this example we are subtracting. Okay, so say we are measuring something on a scale, and the object and the weigh boat weigh 3.66 grams, and if we measure the weigh boat by itself, it weighs 1.4 grams. So to get the mass of just the object, we need to subtract those two values. All right, so we're going to have 3.66 grams minus 1.4 grams. All right, and so again, we see that the first digit has 2 places after the decimal point, and that second value only has 1 digit after the decimal point. So according to our rule, our answer can only have as many as the fewest number of decimal places after the decimal point. So in this case, all right, this number has the fewest places after the decimal point. And so we need to round our answer to match that. We need to round our answer to have only 1 digit after that decimal point. So instead of 2.26 grams, okay, we have to round it to just 2.3 grams. Okay? Because again, according to our sig fig subtraction and addition rule, we can't have more digits after the decimal point than the measurement with the least digits after the decimal point. Okay? All right, so let's take a look at the very last section of these notes when we're multiplying or dividing numbers. Okay, so last but not least, what do I round my answer to when multiplying and dividing numbers? Okay, so this is a little bit simpler than adding or subtracting. We don't care about the decimal. All we care is how many total sig figs do each of the numbers that we're either multiplying or dividing have, because your answer has to have the same number of sig figs as the measurement with the least number of sig figs. Okay, so it's like that famous quote, "You're only as strong as your weakest link," right? Well, numbers or your answer can only be as significant as the digit with the least significance. Okay, so let's take a look at a few examples. Okay, so in our first example, we have 2.54 centimeters times 1.0 centimeters. This is going to be 2.54 centimeters. However, when we take a look at the number of significant figures we have in each of these measurements, we'll see here that the first number has 3 sig figs and the second number only has 2 sig figs. So our answer can only have 2 sig figs because our weakest link here is the second value with only 2 significant figures. Okay, so instead of 2.54 centimeters, we actually have to change that. We have to round it down to 2.5 centimeters. Okay, because again, our answer can only have as many significant figures as the one with the least amount of significant figures. Okay, so that least amount here was 2, and so our answer can only have 2. Okay, so if we take a look at our second example, we have 3.57 grams divided by 1.230 milliliters. Okay, so we're doing a little density problem. So if we take a look, we count up the number of sig figs in the top number. We have 3 sig figs. There's no zeros, so all of them are significant. And in the bottom number, we do have a 0, but it is a significant 0. Okay, it's not a placeholder. We have a decimal here that's present, so we start counting from the Pacific side. We count all the digits starting with the first non-zero digit. Well, in this case, the first digit is non-zero. So we start there and we count everything behind it. Okay, so in this one, we have 4 sig figs. All right, so if we have 3 sig figs on top, 4 sig figs on the bottom, our answer can only have as many as the least. So our answer must be rounded to 3 significant figures. So when we do this calculation, we have to round our answer to 2.90 grams per milliliter. Okay, because again, we have to have the least number of sig figs in our answer, because we can't be more precise than the least precise measurement. All right, so that's all for these significant figures, and I know it's been a kind of a long homework assignment with the last notes and these notes, but tomorrow is going to be lots and lots and lots of practice with this stuff. All right, so we'll see you tomorrow.